Recently, the discovery of a purported biosignature on Mars made headlines. This was greigite found in the Jezero crater, which itself is located at the western edge of the Acidus Planitia, a larger impact basin. Greigite is an iron sulfide mineral with 2 iron and 4 sulfur atoms. The sulfur atoms are all in a reduced state, but one of the iron is reduced, i.e. iron 2, and the other is oxidized, iron 3. Greigite can be formed by a variety of ways, both biotically and abiotically. In a biological setting, many species of microorganisms can use either iron 3 or sulfate as an electron acceptor to oxidize organic carbon instead of oxygen as an energy source. The resulting sulfides in ferrous iron will then precipitate out with the remaining ferric iron to form greigite. Interestingly, there was also organic matter found in proximity to the greigite on Mars, indicating that it may have been the product of microbial respiration. Abiotically, it can also precipitate out in an alkaline solution so long as iron 3, iron 2, and sulfide ions are present. This may sound a bit confusing to any of you who have been paying attention to what a lot of astronomy content creators here on YouTube have been saying. The commonly cited claim is that you need acidic conditions for greigite to form abiotically. While alkaline conditions will cause iron to precipitate out as greigite, in order for this to work, you first have to get both the ferrous and ferric irons dissolved in solution. Iron 2 is fairly soluble in water and only precipitates out once you get to a pH of 8.5. However, iron 3 is insoluble and only dissolves in a pH of less than 3.5. So, you don't need acidic or alkaline conditions on their own to produce greigite. Rather, you need a small amount of acidic solution with high concentrations of iron 3 dissolved in it to mix with an alkaline solution with iron 2 and sulfides in it. The rapid rise in pH will cause the iron 3 to precipitate out with the iron 2 and sulfides. The Jezero crater has many features that indicate that it was once filled with water, and the mineralogy suggests that neutral to alkaline conditions were a near constant, and there is no sign of an input of acidic solution near the greigite nodules. To make iron 3 available to use as an electron acceptor, microorganisms will often employ chelating agents which bind to it and keep the iron 3 suspended in solution. If the greigite on Mars is indeed biogenic, this is one possible way the iron 3 present was incorporated into it. There is also the issue of the sulfide present in the greigite. Many hydrothermal environments here on Earth are known to emit sulfides, and we found ample evidence of hydrothermal activity at the bottom of the Jezero crater. However, this does not seem to be the kind that produces sulfides. This would suggest that the sulfides in the greigite were produced via the reduction of sulfate. Sulfate can be reduced to sulfide abiotically using organic carbon as an electron donor. However, this reaction requires high temperatures, which again, the mineralogy doesn't indicate were present. All of this indicates biotic production as the most likely source of the greigite. But in what kind of ecological context could it have been produced? To get an idea, let's look at when these nodules were supposedly formed. You may have heard that ancient Mars was wet, but there were 2 main periods where much of the Martian surface was covered with water. The Noachian, from 4.1 to 3.7 billion years ago, and the Hesperian, spanning from 3.7 to 3.2 billion years ago. During the Noachian, Mars experienced regular rainfall, comparable to what we see on Earth today. Mars was also getting pelted with asteroid impacts, and the precipitation would have filled most of these with water. It's hypothesized that an ocean also covered the northern lowlands during this time. During the Hesperian, rainfall was much rarer, and most of the craters would have been empty, but we are pretty certain that another large body of water called the Deuteronilus Ocean covered the northern lowlands. Jezero crater formed between 3.7 and 3 billion years ago, putting its age of formation mostly in the Hesperian. It's currently unknown whether or not the Deuteronilus Ocean extended into the Acidus Impact Basin, but we are certain that the water which filled the Jezero crater was its own separate body. While most Martian impact craters wouldn't have been filled with water 3.5 billion years ago due to the lower precipitation rates, the Jezero crater is in a unique geographic position. Global patterns of precipitation on Earth are largely driven by Hadley circulation, and it's likely that this was the case on ancient Mars as well. However, while Earth has 6 Hadley cells, Mars probably only had 2 due to its smaller size, one in the north and one in the south. As air flowed near the surface, it would move in a polar to equatorial direction. Near the equator, it would be heated sufficiently to rise, during which time it would be cooled. This would result in the water vapor in the air precipitating out and falling as rain. In the upper atmosphere, the air would then flow in the opposite direction. Once it reached the poles, it would be cooled sufficiently to sink, flow near the surface, and the cycle repeats. On the northern hemisphere, the air flowing along the surface would collect far more water vapor than it would in the southern hemisphere as it passed over the Deuteronilus Ocean. Close to the equator, the surface airflow in the northern hemisphere would arc westwards due to the Coriolis effect. This would cause air moving over the vast Utopia region to flow toward the western edge of the Acidus Basin where the Jezero crater is located. Here, there's a sharp increase in elevation, which would push the air higher at a greater rate, causing the air to cool faster, and in turn cause the water vapor to precipitate out more rapidly, resulting in a rain shadow effect. So, while the Hesperian Mars experienced far less precipitation than the modern Earth or the earlier Noachian, the Jezero crater was one of the few locations where it rained regularly. You may have heard that the Greigite nodules formed at a time when Mars was quote-unquote dying, but this isn't as bad for life as you might think. When astronomers say Mars was dying at X time, what they are usually referring to is the weakening of its magnetic field. Without the protection of said magnetic field, the solar wind would start to erode the atmosphere, which, over time, caused Mars to go from having an atmospheric pressure comparable to the Earth to the thin wisp we see today. Apart from thinning the atmosphere, the solar wind would also have an oxidizing effect. Despite how oxidized its surface is, the Martian mantle is more reducing than that of the Earth, indicating that the atmosphere of the Noachian Mars was more reducing than that of the primordial Earth. When the solar wind began to erode the atmosphere in the Hesperian, water, methane, and ammonia molecules would be split by radiation, and the lighter hydrogen atoms would fly off into space due to their lower mass. Meanwhile, the remaining oxygen, carbon, and nitrogen atoms would recombine as diatomic nitrogen, carbon dioxide, and diatomic oxygen. This oxygen would then react with iron on the surface, forming rust. At this time, much of the Martian surface which formed during the Noachian would have gone from a dark gray to a rusty brown color. The land on the west side of the Jezero crater is Noachian aged, suggesting there were iron oxides which would have been washed into the bottom of the crater where microbes could have used them as an electron acceptor in respiration. But what about the sulfur in the Greigite? How did it get there? Volcanic activity was still pretty common during the Hesperian, and this would have released sulfur dioxide into the atmosphere. This will nominally react with water in clouds to form sulfite. This compound is highly reactive, so when it rained down, it would usually react with various minerals on the surface, taking it out of the solution. However, with trace amounts of oxygen being produced abiotically in the Hesperian, the sulfite would react with oxygen in the clouds, forming sulfuric acid and its conjugate base sulfate. These compounds are far less reactive than sulfite and would come down with the rainfall into the Jezero crater. Here, Microbes could again use it as an electron acceptor in respiration, with the resulting sulfide ions being incorporated into the greigite. While we know iron and sulfur-aspiring metabolisms exist, are they likely to have come about this early on Mars? To get an idea, let's use the Earth as a reference. The Noachian and Hesperian periods roughly correspond to the Eoarchean and Paleoarchean eras of the Earth respectively. During the Eoarchean, the only element we see isotopic evidence of life using is carbon. Hydrogen gas released from hydrothermal systems can be reacted with atmospheric carbon dioxide to form organic molecules. This reaction also releases energy, which life can utilize in its metabolism. However, 3.5 billion years ago in the Paleoarchean, we see evidence of sulfur respiration in the form of sulfides much more depleted in the heavier sulfur-34 isotope than those produced abiotically. 3 billion years ago in the subsequent Paleoarchean, we also see evidence of iron respiration. In banded iron formations from this time, we see a mix of magnetite and hematite. All of the iron atoms in hematite are fully oxidized, i.e. iron 3, while in magnetite, there are 2 iron 3 ions with 1 iron 2. This makes it somewhat similar to greigite, with the sulfur switched out with oxygen. Some of the magnetite nodules in Mesoarchean banded iron formations have carbonate inclusions, which are much more depleted in the heavier carbon-13 isotope than most carbonates. Organic matter has less carbon-13 than other sources, suggesting that these nodules were produced by oxidizing organic carbon using the iron 3 in hematite as an electron donor, resulting in iron 2, which was then incorporated into the magnetite. So, we can say that sulfur and quite possibly iron respiration were present on the Earth when the Martian greigite nodules formed, further leading credence to them being biogenic. I think there's an elephant in the room. Where did the organic carbon the iron and sulfur-reducing organisms supposedly oxidized to form the greigite come from? In the Jezero crater, we find evidence of ancient serpentinization reactions. Here, ultramafic rocks like olivine and pyroxene react with water to form magnetite, serpentine, and hydrogen gas. Microbes can react this with carbon dioxide to form organic molecules, and, as previously described, this metabolism likely emerged on Earth even before the Jezero crater formed. So, we can say if there was life, there was certainly a way to produce organic carbon. But what about other mechanisms of biotic production? On Earth, we find evidence of photosynthesis in the form of ancient microbial mats known as stromatolites, dating to 3.5 billion years ago. But instead of using water and producing oxygen, these early photosynthetic organisms likely used sulfides as an electron donor, releasing sulfate. Around 3.2 billion years ago, we see the aforementioned banded iron formations appear. There seems to have been no or highly limited oxygen production during this time, but one hypothesis is that photosynthetic organisms used iron 2 in the water column as an electron donor, producing iron 3, which then precipitated out as rust. So again, we can say sulfur-based photosynthesis and possibly iron-based photosynthesis was present on Earth at this time, suggesting that both metabolisms could have been active in the Jezero crater. If this was the case, respiring heterotrophs could use sulfate and iron oxides washed into the lake at the bottom of the crater as electron acceptors to oxidize organic carbon. While some of the resulting iron 2 and sulfides would have been incorporated into the greigite nodules, most of it would go back into the water column. These could then be used by phototrophs as an electron donor to produce organic carbon. The phototrophs would then release iron oxides and sulfate, which the heterotrophic respirers could then use, and the cycle repeats. So, there could have been a proto-carbon cycle on ancient Mars, except one based around iron and sulfur instead of oxygen. However, this is all based off early life on Earth, and it may very well be that Martian life, if it did indeed exist, followed a very different trajectory. This is a constant dilemma astrobiologists face. We want to use life on Earth as a reference because it's the only one we have, but with a sample size of just one, we can't say how representative of how likely such a biosphere is to form in the first place life on Earth really is. So, if I was to speculate as to what alternative possibilities there are, one hypothesis I could come up with is that instead of photooxidizing another element to reduce carbon dioxide, Martian phototrophs use light energy to combine atmospheric methane and carbon dioxide into organic molecules. Meanwhile, heterotrophic respirers in the Jezero crater would have been solely dependent on the influx of exogenous sulfate and iron oxides to act as electron acceptors. In this case, only minor nutrients would have been cycled between the phototrophs and heterotrophs. But, in whatever ecological context it formed, the discovery of the Martian greigite remains a tantalizing insight into both what the red planet was like in the ancient past and the possibility of life elsewhere in the solar system.